All right. Okay, so the recording would have started. We're just doing a recap, right? Just to close off and to solidify our approaches, our work. All right. So in terms of searching, we identify we have two searches that we must know for CAPE exams: binary and linear. Sorting, we have bubble and selection. Okay. So if it is, and you all have to interact with me here. All right. So I'm going to ask some questions. Let's say, for instance, I have an array. And I have an array, and this array has, right, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. And of course, we have our array subscripts 1, 2, 3, 6, 7, 8, 9. So we have our array subscripts. And we have the values inside of this array. And we have 1, 19, 27, 35, 36, 42, 81, 91, 97, and 101. And it just so happens that the values inside of this array is, the values inside of this array are in ascending order. If I ask the question, using each type of search, we have a linear search, and we have a binary search. And this is a question to you all to think about and answer now. If it is that I was looking for the search key 93, all right, using either search technique, how many comparisons must I make before I can realize that that 93 is there or not there in the search array? Using, these different search techniques. How many comparisons would I need using either search technique to make make a statement about whether or not the search key is in this array or not? For the linear, it should be an easy answer.
So for linear, you just go the whole 10. And
yes.
Which is or something.
For the binary, it will be what?
So for linear, it is search the whole 10, and if it doesn't find it, you'll pause the statement.
Right. So we can say that after 10 arrays, so we established that 93 is not here. But for the linear search, we had to make, right, after 10 comparisons, we agree that after 10 comparisons, we agree that the value is not there. Correct? Yeah. And for the binary, I know that we might have to make some, do some operations to work out the binary. Has anybody worked out the binary and could tell us how many comparisons would it take for us to know if 93 is in this array using a binary search or not? Take your time. I'll give you 2 minutes.
Sorry, repeat what I said.
We want to know how many comparisons need to be made for the binary search to tell us that the value is or is not in the array. Are we working it out or are we lost? We have to perform a binary search here.
Okay.
About how much?
3 or 4, sir.
Right, so we can make a guess that in about 3 or 4 steps we could establish whether or not the binary search is in the array, because for us to do the linear search, we just simply compare each value against 93. And this one doesn't work, this one, no, 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 no. But with the binary search, we can't make an assumption that because this is this particular array is in ascending order, that it can't be, it's not in the future. So we do have to check against these two. And this is how we know that we did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 comparisons. And we could say for sure, for certain, that it's not in the array, right? Everybody understand that for the linear approach, yes?
Yes, sir.
Good. So now we're taking the binary approach, and the binary approach, of course, is a much more efficient approach to finding out whether or not a value is inside there. And for us to do the binary approach, the first thing that we have to do is what? Some of y'all told me that you all understand the concept of the binary search. So if it is that I am asking you to walk me through, let me call a name, right? And I'm going to call Sachin. Sachin, you there? Sachin? All right. Sachin is not with us apparently. Jaden. Amazing how everybody's microphones start to give trouble when I start to call names. Jaden, are you there?
Oh, so yeah, I was talking. Sorry.
All right. I'm
Yeah.
hearing you now. All right, Jaden, could you walk me through taking a binary approach to finding out whether 93 is in this array or not? What do I have to do?
So the idea is just take out a few of the, not a few, but the ones in the
Jaden, you're going silent again. All right, so let me walk it through. For our binary search, the first thing that we need to do is to set the first element as our start element and the last element as our end element. We take a look at the sum of the start and the end element, and we add them together and get the value of the middle element. So 0 plus 9 divided by 2, right, after dividing by 2 will give us the value of 4. So our first middle element is 4. And what can we compare the value in the middle element against the search key. So we compare 93 against 36. 93 will never be in this first half because this first half of the array, this first half of the array is all smaller than 36, and 36 is smaller than 93. So we know that everything from this middle value back is not compatible, it's smaller. There's no chance of finding the value inside of here. So what we do is that we condemn this section, and then we make a new start value here. So in terms of our new start value here, right, our new start value is now 5, and 5 and 9 is what? 5 and 9 is 14. 14 divided by 2 is 7. So our new middle value is 7. I compare 93 against 91. And again, I come up with the same conclusion. Right? I can come up with the same conclusion. 93 is larger than 91. So we had one comparison. So comparison 1 was against 36. Right? And that didn't match. Now comparison 2 is against 91, and that didn't match. So what do we have to do? Again, because 93 is larger than 91, we know that there is no way between the start value and the what is now the medium value, we're going to find any value inside of there. So we now make the value following here to be the start value. Okay? So we know that nothing before the start value is going to be 93. 8 and 9 together is 8 and 9 is 17 divided by 2 is 8. So our middle value and our start value now happen to be the same thing. But when I compare 93 against this current middle value, it's now bigger than the search key, which means that nothing afterwards is going to be matched. So nothing afterwards is going to be matched. So what do? We have to now make the one before the middle value our new end value. So the comparison 3 was on 97, and that didn't match. And now the end value is now larger than the start. Okay, so the end value is now larger than the start, which indicates that there are no values for us to check. So at this point, we can safely say that 93 is not in the array. So whereas it took us 10 comparisons, in general for a linear search to find out that we don't have a value inside of there, right? It took us 3 comparisons using the binary search to find out that this is not inside of here. The only thing that we must ensure is that for a binary search, the data being searched must be sorted. Everybody is cool with that?
Yes, sir.
No problem.
Yeah.
All right. So we can go on now and talk about the sorting algorithms, yes? Bubble and selection sort. Yes or no?
So yeah, I don't mind.
Anybody have any further questions on the linear and binary approach? We have to be able to put this into code. All right, we have the code for it, but it's just about understanding the steps that we have to take. So how do we code creating an array? How do we code assigning the start element to the beginning of the array and the end element to the end of the array? Okay, how do we code working out what is the middle value inside of this array? Everybody with me on that?
So that was a question? Or
No, I just talking through.
oh, okay.
All right. So we have 2 types of sorting as well. Okay, so we have sorting, and we have 2 types of sorting, and they're both equally horrible. Right? Not equally horrible. Bubble is like worst possible, right? Selection is just a little better. And then there's another sort that is kind of like selection, but it's called insertion sort. I don't know if any of you have watched the video that I sent to you on the sorting, just generally talking about sorting. They didn't use in that video I sent in the chat group. They spoke about the bubble sort, and we established that the bubble sort is probably the worst possible way to try and sort a value. Yeah? You all watched the video?
So repeat what you said real quick, please.
Did you all watch the video that I sent in the WhatsApp chat? You don't hear cracking up. Nobody watched my video. Nobody want to say they didn't watch my video. Right?
No, you sent a video.
You didn't even know I sent a video? Wow.
But I'll go and watch it now.
No, watch it now. Now it's time to watch me in class. Watch it after class. I sent it after class last week. Right? Okay, so you all will just make sure and watch the video. The video spoke essentially, it compared I believe it was bubble sort, a sort called insertion sort, and it compared another type of sort, bucket sort, I believe it was, in terms of showing how efficient how you could improve efficiency with different types of searching, with different types of sorting. Okay, it showed how many times, using a real life example, if you had a whole bunch of books to sort and you had to sort it for a library, it told you how long it would take to sort the books if it is that each action that you took towards sorting took a second. If it is that you had the bubble sort, and I think the size of the books in the video was 1,000 books, each action inside of the bubble sort would, let's say, would take about 1 second. They estimated that it would take close to 9 days to sort all the 1,000 books that you have in the library. Okay. If it is that you use a second sorting method, which is kind of similar to the selection sort, but it's a bit of reverse selection sort if you want to think about it. It's called the insertion sort. That insertion sort cut the time down from 9 days just by changing your approach to sorting. It cut the selection sort down to from 9 days to about 3 days, where each activity is a second of sorting. All right. And then if it is that you had I think the third one was the bucket sort, and they explained the different sorting techniques to you. The bucket sort approach, was it the bucket sort or the quick sort, boy? I can't remember exactly whether it was the bucket sort or quick sort, but the video is there to watch. I'll send over the link if you all want to really watch it. That sorting technique, where you break up the sections to be sorted into smaller subsections, actually took less than a day to complete the sort. So it just kind of went through, how you could improve efficiency by shifting your approach when doing a particular sort. All right, I would suggest that you watch it because I wanted to also touch on a concept called Big O notation, which I would still do today, but that video kind of wanted to lay the foundation for it. Okay, I know that sometimes it is hard after a computer science class to then go and watch a computer science video. But I mean, especially for those of you all who want to continue along the route of computer science, there's a lot that you know, generally I would say you need to kind of always be curious and questioning things why. You always have to ask why about concepts in computer science. So I would suggest to you all, don't wait for me alone to speak about something. And there are a lot of what I would call very casual videos about different aspects of computer science. I watch everything on, ranging from games and what new technologies they put in games. So sometimes I have a graphics card in my laptop. I'd say, okay, well, I see in some letters after the name of the graphics card. What does that mean for the graphics card? And I'd look it up and I'd see what it could do. I mean, I might even use it, but I'll look it up at just a question that I have, right? Sometimes I would sit down and I would think to myself, well, exactly why one sort would work better than the other. There are thousands of videos on YouTube about that. Okay? So casually lend your attention to something partially educational about what you're studying. You could just, again, there are a lot of people, I know that I mightn't be the most exciting or whatever, but there are a lot of people who can make it exciting, and a lot of channels that carry these things. So that's just my advice to you all. I know I went off on a ramble there or whatever, right? But using the one person who's here as a gauge as to the level of interest, and he's actually in school. Oh my God! All right, so right, so we have sorting, and we have the bubble sort, and let's just take a look at how we, true sense to the bubble sort. Let's take a look at, let's say, something that is mostly sorted, let's say, backwards. All right. We have an array or a list of values. Not tree. 90, 20, 17, 4, 65, 2. And we want to utilize a bubble sort to organize this list of values. All right, we want to utilize a bubble sort to organize this list of values. So, I'm gonna spread these out. We want to run through from start to end utilizing a bubble sort approach. Can anybody just give me a fair idea of what the bubble sort approach entails? From your understanding.
You will take the first number and compare it with the next number, and if it's lower or higher, it will either take that place or it will stay in the same place.
Right. Thank you, Josiah. So the bubble sort compares two values, the value that you're currently at and the value that is right after, directly after. And if the value that you're currently at is higher than the value after it, and your objective is to ascend, then you swap those values. So now the larger value is going to be on the right-hand side. And then you move to where you swap that larger value and you do the same thing for those two values, that value now and the value right to the right of it. And you compare and you swap if necessary. If not, then you move to the value to the right and you swap. So we always move into the right and swapping. And so let's just run through. We're running through this whole 6 values here just to see how long it's going to take us if we had if we had to do this bubble sort, to the point where we have to sort out everything. So I'm going to write the you know, the bubbles, the sorts in green, and let's see what we do. So we say 90 and 20. Do we swap those? Or we currently at 90. Do we swap those? Yes. So we'll end up with 20, 90, 17, 4, 65, and 2. Then we still on this 90 here. Do we swap 90 and 17? Yes. So we have 20, 17, 90, 4, 65, and 2. We have this 90 here. Do we swap? Yes. 20, 17, 4, 90, 65, 2. Okay. We have the 90 here. We swap that 90 and 65. We have this 90 and 2 here. We end up swapping them as well. So we end up with 20, 17, 4, 65, 90, and, sorry, not 90, 2, and 90. And now 90 is in this position here, the biggest position that it could be in. And we have nothing to compare it against. So we've bubbled up the largest value to where it's supposed to be. And this is the end of what we call the pass one. Okay, end of pass one. So this is for the truest bubble sort. This is just one pass. Look how many operations we had to do. We only have 6 values inside of this. And the thing that we have to note, and this is kind of like the foundation for what I will tell you about big O notation, which I'm going to speak about in a little bit. The foundation for big O notation is that, you know, you're looking at, do things get more complex? Do things get more complex with the more elements that exist within it? Okay, and big O notation could get a little complicated to think about. All right, but I just want to keep it simple. In terms of sort arrays, right? We have a poor relationship in terms of size and time for a bubble sort, because the relationship for size and time for a bubble sort means that the bigger that a bubble sort gets is the more time it is going to take to for a computer to actually perform a bubble sort on a list of elements. Okay, so just think about it like that, because and we'll see it. Because if it is that this value is 10, we're going to see a lot more operations having to be done to get to the end of pass one for an array with 10 than it had with an array with 6. And you'd see if this array only had 3, we could bubble sort it very, very quickly. Okay. The next thing that we do, so we back to here, and we have to start back now for pass 2. Pass 2 starting from 20. So pass 2 is starting at 20. Let me put it in a different color, right? So we start in pass 2 with the red, and we swap in 20 and 17 because 20 is larger than 17. So we have 17, 20, 4, 65, 2, and 90. Then we're looking at this one here. This 20, we comparing that 20 with 4. Okay, so we end up with 17, 4, 20, 65, 2, 90. Then we have the 20 here. We looking at 20 and 65. No swap needs to be made there. 17, 4, 20, 20, 65, 2, 90. Then now we on 65, we're comparing it against 2. We have to swap. 17, 4, 20, 2, 65, 90. And now we're comparing 65 and 90. There's no need to swap there. So we end up with 17, 4, 20 to 65 and 90. And now, because we are at end here, we are at the end of pass 2. And now we can continue on by starting over for pass 3. Okay, 4 and 17, we swapping this. I know that I'm taking the time. We're going through everything here. We're looking at how bubble sort works. It's not even a modified bubble sort. This is bubble sort in its purest code. It checks everything every pass. Okay, 17 and 4. 17 and 4, we swap that. So we end up with 4 here, we end up with 17 here. 20 to 65, 90. Then we move to here, 17 and 20. Should we swap? No, we don't need to swap because 17 is smaller than, right? So we end up with 17, 20 to 65, 90. We are here, 20 and 2. Yes, we should swap there. Okay, so we're moving up the 20. So we say 4, 17, 2, sorry, 20, 65, 90. We're comparing 20 and 65. We know that 65 in its place, 90 in its place. So we don't have much to change here. So it's going to be 4, 17, 2, 20, 65, 90. Okay, and then 4, 17, 2, 20, 65, 90. And then we'll end up at the end of pass 3. And the end of pass 3 is what we'll use to feed the beginning of pass 4. And I'm going through this to just show you all how inefficient this algorithm actually is, right? 4, 17, 2, 20, 65, 90. 4 and 17, they're good where they are. So we end up with 4, 17, 2, 20, 65, 90. And again, we have the 17, 17 and 2 will swap. So we end up with 4, 2, 17, 20, 65, 90. We have 17 with 20. Well, we know everything up to this point is fine. So I'm just going to write it out. 4, 2, 17, 20, 65, 90. All right, 4, 2, 17, 20, 65, 90. 4, 2, 17, 20, 65, 90. And then we come to the end of pass 4. Okay, this is this algorithm is not optimized. Okay, and then we're going on the last one, our last journey through. So again, we compare 4 and 2, we end up with 2, 4, 17, 20, 65, 90. And we don't really have anything to change after this, right? So it's just going to end up being going through 2, 4, 17, 20, 65, 90. 2, 4, 17, 20, 65, 90. And 2, 4, 17, 20, 65, 90. End of pass 5. So after all of these operations here, we end up with our sorted value, right? When in reality our array got sorted somewhere around here. But I mean, look at how many steps it still took to get to that point. Okay, so there's a lot of work to be done, a lot of sorting, and this is only 6 elements inside of here. All right, so this is not really an efficient way of sorting because the bigger the list that we have is the longer it's going to take us to be able to sort through everything, etc. Everybody with me? Josiah, when I say modified bubble sort, I mean where we can remove, you know, where we put the value to remove the values that we accounted for. So in a modified one, we would have said, okay, well, 90, we've gotten 90 here. So don't do this last one because we know 65 and 90, there was not going to be any swap there. When we get 65 in place, we'll stop at this point. So we'll say, okay, don't compare 20 and 65 or 65 and 90 because we know that they're in place, right? Same thing for when we hit 17, same thing for when we hit 4, and that's it. That's what I mean by where we modify the bubble sort. We are now seeing this message here. All right. So any questions on this? Any questions on this?
So nothing much, just long and well, that basically it's
Yeah, I know it was long to go through, but I feel like sometimes the best way to go through it would have been like this, so that at least we are very aware that you know, this is what the bubble sort will entail.
So what is
Yeah.
this used for again? Like
Sorted.
Yeah, I know, but
sort.
like this specific sorting, this bubble sort, like
It's
if
a
any-
technique. So let's say, for instance, you have an array of information that is sorted, and you want to, let's say, it's not much information ever at any one point in time, but you want to sort it out. It's a good way to sort small values. But if it is that you have larger data sets, then this might not be the approach that you want to take for sorting information. So it's not that it's not useful, you know. It is useful, but you have to, it's useful depending on the scenario. You follow me?
yes, sir.
So, you know, it's let's say, for instance, you're doing a mock-up of some system that you have. Maybe it's a prototype or something like that. And you just want sort functionality to show that, okay, this will be sort functionality. This is the prototype. I just want the prototype to work. I'll do a quick bubble sort. But in terms of maybe when the system is much better defined, then you would be able to probably put in a much more efficient sorting algorithm into the system, because you know, okay, I'm not just dealing with 100 values for the purposes of a demo. I'm dealing with 500,000 values because this is somebody's actual data in production. With me?
Yes, sir.
Yeah. All right. So the next thing that we're going to look at is, hold on, I'm just waiting for this right. The next thing that we're going to look at is the selection sort. Which is slightly better than the bubble sort. Let's be honest. And it's better than the bubble sort because by the nature of the selection sort, each iteration searches smaller and smaller data sets, as a smaller and smaller subset of the original data. Whereas in the truest sense, the bubble sort will keep on going over all of the data that it's supposed to go. Even sorted values, etc. Right? And even where that doesn't happen, I think that the selection sort is still slightly better than the bubble sort. I do know that the bubble sort is, I believe, the worst possible sorting approach to take, especially for large data sets. All right. Right. so our selection sort. How does our selection sort work? Oops. How does our selection sort work?
I think you take the smallest value within the array and you swap it with like the first position in the array.
Yes. So again, let's take the value of let's take an array with values 90, 51, 2, 7. Why I keep on putting so much space between it? 51, 2, 7, 9, and 1. So we have some values inside of our array, and our selection sort tells us that we have to mark the current value that we're at. And we have to mark the current value that we're at as the smallest value. And the objective is to compare each value against the known smallest value. And if it's smaller, then we mark it as smallest. So we're comparing 51 against 90. We'll mark that as smaller. So 51 now becomes our smallest value. Then we mark 51 against 2. That's smaller, so 2 now becomes our known smallest value. 2 will mark against 7. Is 7 smaller than 2? No. 2 will mark against 9. Is 9 smaller than 2? No. 2 will mark against 1. Compare against 1. 1 is smaller than 2. So once we reach the end and we've confirmed our smallest, we're going to perform a swap. We'll swap the smallest with the current. So after our comparisons, our swaps would be 1 and 90 with 51, 2, 7, and 9 in between. And now our current value and our smallest value gets reset to the next value, 51. So again, we compare 51 and 2. 2 is smaller. So 51 is no longer our smallest value. We compare 2 and 7, not smaller. 2 and 9, not smaller. 2 and 90, not smaller. So what do? We swap. We say, right, that 51 and 2 have to change places. So we end up with 1, 2, 51, 7, 9, and 90. Then we move to 51 again as our current and our smallest. And we end up comparing 51 against 7, known smallest. 7 against 9, no. 7 against 90, no. So we swap. 1, 2, 7, 51, 9, 90. And again, we end up with the 51 being the current and the smallest. 51 and 9, 9 is the smallest. So we make that the smallest. And we compare 9 and 19, no marking over there. So we swap. So we have 1, 2, 7, 9, 51, and 90. And then again, we have this is current and the smallest. 51 is not smaller than 90. So the last swap is 1, 2, 7, or the last lack of a swap is 9, 51, and 90. And this is it. How much swaps did we do there? We had 1, 2, 3, 4, 5 instances where we had to swap values. Or in terms of six steps, essentially, right? Where we had to check and see if they are swaps or if they're not going to be swaps. Compare that to what we did just now. This was essentially hell in comparison. Do you understand where I'm coming from now? In terms of if we look at the swap operation, the need to swap and the need to, swap based upon comparison. In this instance, if you put 1 mark for swapping, 1 mark for comparing, 1 mark for swapping, or 1 second for comparing, 1 second for swapping, you're going to end up with a bit more in this instance than you are going to end up in this instance. Because each time you go forward, you compare, you had 1, 2, 3, 4, 5 comparisons and 1 swap. So this was 6. Then you had 1, 2, 3, 4 comparisons and 1 swap. That's 5. So you end up with 6 plus 5 plus 4 plus 3 plus 2 plus 1. You all understand?
Yes, sir.
Yes, sir.
Whereas here, for each comparison and swap, you had 1 comparison and 1 swap. 1 comparison, 1 swap. 1 comparison, 1 swap. And you're doing that almost right all the way down. So, we need to, we can add up how many activities it takes for different sizes of arrays. And I feel that might be a really nice assignment for you guys to do. Okay, don't mind. I know that I'm saying the A word, their assignment. All right, but allow me. And when you compare it, we'll end up seeing how many, it's like, sir. Okay. But we'll end up seeing how many, how efficient we are. And, I think that's good for understanding selection and sorting. Any questions at this point before I give you a little 5-minute break? All right, so I'm going to pause the recording.
So you're looking sad.
Yeah, because I hear all alone. It's just, it's not for this one guy here. I'd have been like, well, classic, who want to see me? We trying, but how much weeks now we can't see each other? Could we agree that next week, Monday, we will be here? Wow, nobody answers like yes or.
So if we knew we had class this morning, we would have been there. Okay?
I hear you. But it was in the calendar. It was.
So was it really? You had to ask yourself, so was it really Nickel? No.
Was it not?
I don't know. Honestly, I don't know.
He already waste. That's fine. Again, it's all on me. Hold on, eh? All right, so it's all on me. So I'll take blame for that. All right, so we're going to just talk about the big O notation. The big O notation briefly. I will. Okay, if it is that you're Googling, and please Google big O notation and don't leave out the word notation. All right. So it's big O notation is the way that it's referred to. And essentially, this is just to define it quickly. We don't need to go into the nitty-gritties of it. Okay, because big O notation could get a little complex in terms of understanding, but this is all we need. It's a measure of the execution of an algorithm. And you're looking in terms of what the algorithm needs in terms of either time or memory as a resource. And you're looking at the size n, which is the number of items in the algorithm. So it means that you know, essentially looking at how much time or resources is utilized as the value of n increases. Okay, so we have the way that the notation is read is, you know, it's f of n is big O of g of n. Okay, and what we really mean there is saying that, you know, the bigger that the number of items is really and truly the more of some sort of resource that we have, time or resource that we need. Okay. There's a site called bigocheatcheat.com that kind of shows the complexity chart. We have a couple different ways of representing big O complexity. And well, of course, what's in red is horrible. Okay, so if it is that you have a function and the function maps on to where we have O is n factorial. It means that, you know, the amount of operations that it takes for elements, as the elements increase, the operation sharply increase. So it's going to be like, you know, it's going to be very few operations is going to start to take up a whole lot of resources. Then you have as well O is 2 to the power n and O is n squared. All three of these, they tend to, you know, in terms of return, they tend to be bad. And we will actually look at where the bubble sort and the selection sort fall in terms of being linked to this operation chart. Okay, so if it is that we have operation that, you know, could be represented in terms of O n log n, these are bad, but, you know, it's not like unusable. What it's saying here is, okay, there's a relationship that the more elements that you have, it's kind of like maybe like close to a one-to-one relationship or somewhere approaching one-to-one relationship in terms of elements and time. So if it is that we have 1,000 elements, it would take like 1,000 seconds. Whereas for O2 to the power of n, right? If we look at that, if we have 1,000 elements, then it means that the amount of operations would be like 2 to the power of 1,000, which is a huge number. Okay, or even 1,000 squared. That's to operate for 1,000 elements, it's going to take 1,000,000 seconds. That's, you know, that's not really good. I mean, when it's small, if it is that you have, you know, 3 elements, it takes 9 seconds. If you have, you know, 10 elements, it takes 100 seconds. But 1,000,000 seconds is a lot of time, right? 1,000,000 seconds, I think, is close to 11 days. So, you know, that for an operation that has a complexity of O n squared, it's bad. Okay. If it is that we have complexities, right, that are like O to n, okay, so, you know, we have that's a one-to-one relationship basically there, sorry, more like it, right? O to the power n, whatever n is, it's going to take that amount of operations to work out. And down here we have O log n, no, O is a constant, like O is 1. Or if it is that we have a constant like O is 3, it doesn't matter if your n, your n, which is number of elements, is 5 persons, it takes 10 seconds to do. If it's 50 persons, it takes 10 seconds to do. If it's 5,000 persons, it takes 10 seconds to do. Right? You could think of it as like an easy way of thinking is like telling somebody no. It's telling somebody no. Okay? I mean, it doesn't matter the amount of persons that ask you to do it, if 3 people come to you and say, your answer will always be no, then no. 3 people doesn't translate to more than 1 word. Okay? So this is kind of like the complexity chart. Of course, you want algorithms when you're looking at efficiency, and the study of efficiency is a whole branch of computer science in itself, especially with respect to getting computers to do more and more in less time. Right? Getting computers to do more and more in less time. As some of you all might be familiar with the P is equal to NP. That's one of like math's biggest problems. If you could prove that, there's a $1 million prize for you or something. So that's something, again, you could look up on YouTube. And it's something that you would see if it is that you decide to research the big O notation, you would see that P equal NP kind of comes up as something related to this. As in, okay, for a set of problems, can those problems be solved in a manner that where the more issues that you have, it doesn't take a obscenely increasing amount of time. All right. One of the issues that people often use for that P equal NP as an example is like the salesman problem. I don't know if you all know that one, with the salesman who has to go to different cities, and could you work out the best path without having to see all possible routes of all the cities? All right. But in terms of big O notation and big O complexity, if we're looking at sorting algorithms, we have some 2 things in terms of time complexity and space complexity. Okay, and if it is that you see the bubble sort in terms of time complexity, our bubble sort falls into that bad range on average or worse. Selection sort as well falls into that bad range on average or worse. Okay, so in terms of knowing that our algorithms in terms of increasing the amount of elements that need to be sorted, our bubble sort kind of falls within this range here. Okay, don't study the theta versus the O, etc. Right? There's a little difference between them, but I'm not going into that now. Okay, and in terms of space complexity, well, these are good because it means that you don't need to have an increased amount of space to be able to perform a bubble sort or a selection sort or anything. So, but these are not so good in terms of, on average, they're pretty poor algorithms. I think that the video that I sent you talked about the bucket sort, if I'm not mistaken, right? Talked about the bucket sort, if I'm not mistaken. But bucket sort and radix sort is one you could look into. I can't even remember how to perform it, to be honest, but all of these sorting algorithms, they're out there, they exist. These are some good algorithms to use. So again, it comes back to like what Josiah was asking about in the early of class. And while radix sort might be a little more pressure to implement, radix sort you do need a little more space in terms of if it is that you have to implement it, there's a trade-off in terms of how much computer storage or how much memory or RAM that you might need. Okay, so you notice for these algorithms, you don't have to expand at all on the amount of space that you have. If you have an array of a particular size, you don't need to expand on that. But for the bucket sort and radix sort, there are arrays that you might need to expand in terms of the amount of space that you have. So again, if it is that let's say you're in a small consumer electronic that needs to perform a sort, let's say maybe you have a phone or something, so on. This was the early days of and you want to provide a way to sort your contacts by different, let's say first name or last name or something, it might be easier to perform a bubble sort on that phone. Because I mean, if it is that, let's say they were capped at about 400 or 500 contacts in that phone, and at this point in time, it's harder for us to utilize more, to add more space to be able to do a more efficient sort. Then the user is just going to have to wait 2 or 3 seconds to see all of the contacts in their phone sorted by first name or last name, or probably date entered or something. So as opposed to now where we have smartphones with a whole bunch of space, you know, phones come in with all kind of 8 gigs RAM and all kind of stuff. And, you know, people love fluidity in terms of design and you know, in terms of user responsiveness in their devices. Well, you might implement a fancier sort, and you know, it really and truly you have the RAM or you have the space on the phone to be able to have the sort do what it does, because it has to take up more space than it would have contained all of the information inside of there. Okay, so this is a good site. It's a good site to, I mean, as I said, Big O could get a little complex, but we're not looking at that. This is just for your understanding, and this is for of understanding, well, you know, different sorting algorithms. And if you click on these, I believe they take you to the Wikipedia page that discusses how the sort is done. So if you want to read up on the different types of sort, you can. Just be mindful that the sorts, sorry, that CXC needs you just to know the bubble sort and the selection sort. So if it is that you go ahead and want to read up on it, I welcome that. But just know that you don't write any other sort in the exam other than the bubble or selection, because CXC, that is what CXC is looking to confirm that you know. Okay? Any questions about this?
Nah, sir.
All right. So it's pretty as I say, that site, I'm gonna copy the link into the chat so that you could check it out on your own time. Okay, it's bigocheatsheet.com, and it just kind of goes through, well, what is Big O, and you know, for different data structures. We're not really studying the data structures so much. It's just to understand how Big O and array sorting algorithms have a relationship. Okay, so at best, the bubble sort, at best, in the best of scenarios, the bubble sort could give you, you know, a moderate time complexity or fair time complexity. But on average, both the bubble sort and the selection sort are pretty terrible. Okay, and if it is that you want to, I would encourage you to, you know, write an algorithm and, you know, count comparisons and count swaps, and input different values into it, and you could see now, even in terms of performing a binary search on top of a sorted array. So, you know, you could say, okay, let me see if I perform a selection sort and a binary sort, how many elements or how many comparisons is it going to take before it becomes less efficient than a linear search? Because if I have to now do a selection sort first and then a binary search, the selection sort might take up a certain amount of what do you call this thing? A certain amount of comparisons and swaps, and then my search is going to take up a certain amount of comparisons. And when I add that together, is it that I can have an array of size 100 and okay, my linear search is going to take 100 steps to do? Is it that when I have a sort and a search together, a sort with a binary search together, are those two going to come up to less than 100 steps? Okay, it's just something that you all could look into and attempt on your own, or as I said, I might give it to you as some kind of assignment to do. Any questions before we end class? Well, not before we end class. I just want to talk to you all one last thing, probably introduce the concept of the linked list to you all, and then we can probably end class there. Any questions on the big O notation and big O complexity? No, sir. Okay, fine. Let's move forward. Yes, Hazard.
It might not be that related to big O, but I heard like the size and storage is important too. Because like if you type 5 lines of code, whereas if you type like 15 lines of code, the computer still has to go through all those lines and then after like actually carry it out. So that's how important that is to like actually programming at this level we are at right now.
Well, as a consideration, it's you know, as you said, it has to go through each instruction. So that's why, I mean, you know, and especially when maybe now not so much for regular applications, but if you within the branch, let's say one operating systems or two, you know, you're creating applications for embedded systems where maybe the memory is limited, you might have some considerations to make there in terms of, well, how big the actual application could be, how many instructions have to be carried out. Again, you know, thinking through the most efficient way to perform a task is its own job. There are persons whose job is to constantly research optimization and, you know, finding out the best way to do something. So that's why I always kind of say you all at the start of your journey here. This is you all at the point where you kind of just have to kind of understand how things are done. But then at some point during your degree, etc., depending on what you do, you're going to start at looking at how things could be done better. You follow me? So you would look back and be like, okay, well, yes, we understand how to do X, Y, Z. And, you know, you might have a course that starts to look, I think especially the course data structures looks at those kinds of things. You have two courses if you're in university, data structures and algorithm analysis and design. And those courses are going to start to take a look at things that you have been doing in programming. And they're going to ask you, well, is there any better way to do that? Okay, so, you know, when you get into understanding even like the concepts regarding recursion, etc., and the trade-off that recursion will give you in terms of speed versus storage. And there is almost always a trade-off that you have to make. That's what you're going to have to do, you know? Okay, Hazan?
Yes, no problem.
All right, so the last thing that we're going to talk about is just the concept of a linked list. I'm just introducing it, a linked list. And what is a linked list? A linked list is a dynamic structure. Okay, it's a dynamic structure which allows for a linked list is a dynamic structure which allows for values to be stored and removed. And when we say dynamic structure, it means that it takes up just the amount of space that it needs for the ability to hear myself. Sorry. Yeah, for the ability to hold the elements that it needs. So if it is that you have 30 elements, then that's what you're going to hold, right? It also, as the name implies, it allows, actually it's made up of nodes, and it's connected by pointing to the next node. And it exists in memory. Like everything else, but so we're utilizing pointers. And it's a sequential structure. Okay, it's a sequential structure. Which means that in X, things has to be visualized. If a linked list has to be visualized, then we have a node. And that node is made up of two parts. This is the element of the node to hold data. And this is the pointer to link to the next element. So if it is that I have a linked list and I have to visualize a linked list, and this is where I'll stop today after I visualize this linked list. If it is that I have to visualize this linked list, the linked list would be, first of all, you need a pointer to point to the head of the linked list. So you have a pointer which points to the head of the linked list, the first node in the linked list. And that first node in the linked list, when created, is going to point to null, which signifies the end of the linked list. So if it is that I put a value inside of here, and let's say I store in a list of names, right? So I store the name Jasmine here. And then I want to add a value to my linked list. Okay, so let's say, for instance, we want to insert into this linked list another name, Eden. Okay, we'll end up with the head of the linked list pointing to, one second, yeah, pointing to Jasmine. And that newly created node that should contain Eden, Jasmine will now point to Eden. And now Eden is going to point to null. So we know that the last node in the linked list always points to null. That's how we could tell where the linked list ends. Excuse me for 1 second. All right, I am back. Don't panic. Oh.
Yeah, sir. I was panicking.
Right, that's why I always remember to say, don't panic, because you guys are, if you see Eden in class, you're freaking out right now. Right? It's crazy. All right, so we have this linked list, and essentially it's called a linked list because at the end of the day, when you have well, not a full linked list, because there's really no maximum size to a linked list. But once you have a populated linked list, it'll end up looking something like this. If it is that we have to visualize a linked list. Okay? And the last node always points to null, and we have to keep track of the head of the linked list. So just ponder on this for next class, where we would be looking to implement, delete, and insert nodes into linked lists and manipulate the values of linked lists and print out the contents of linked lists as well. Any questions?
No, sir.
So we all good? Everybody's
So I have a quick one. When I was looking at linked lists, I saw something like something with malloc and something with size. I think that's a function, if you know about that.
yes, malloc size up, yes. What that does is that it evaluates the size of the node, and it actually, remember when I said that you have to manipulate memory? I said that just a little earlier in class, that it exists in memory. You're actually going to have to grab a piece of the memory of the computer, allocate a specific size for the memory, and allocate a specific size for the memory, and really and truly then assign it to either the head, like by pointing to it, or assign it to the previous of the next node. Okay, we will get into that in terms of being able to declare and implement a linked list. It is code that we will have to write.
Right, no problem.
Any other questions? Any other questions? No? All right, well then that's it for you and me today, folks. Have a good class. Enjoy. Anybody turning on the cameras to tell me bye-bye? I'm taking off the... All right. See you, Ryan, waving at me.